We know that a whole forest of trees can beat one tree, but what if we took that one tree and pumped it up? Welcome to this video on classification. My name is Kevin Fiesel, and I'm the proprietor of Catalaxy Services LLC, a consulting firm which specializes in work all across the data platform space, especially SQL Server. The prior video in this series looked at bootstrap aggregation and random forests. We learned that a whole series of weak learner trees can best a single tree. But it turns out that bagging and feature limitation aren't the only techniques we can use to improve the quality of our tree-based solutions. Today, we are going to focus on a separate approach that developed concurrently with bagging, called boosting. The intent of bagging is to give you a set of independent, uncorrelated trees, then let each one vote based on the information it has available. The idea is that we can pick up on nuances in the data more easily that way, leading to better outcomes than a single megatree. Boosting, by contrast, is a sequential technique. So instead of training a lot of small, independent, uncorrelated trees, we train one tree and then re-weight the data to emphasize the points that the prior evolutions got wrong. One of the earliest forms of boosting was called XGBoost, and the paper for it came out prior to that of random forests. In each stage of the training process, we create a new weak learner to compensate for the shortcomings of the existing weak learners. By the way, when I say a weak learner, don't take that in a negative way. What this means in the literature is we expect a weak learner will not be perfect at classifying information on its own. It may be able to classify some things well, other things poorly. We're not necessarily trying to train one single model to rule them all, certainly not in one go. With random forests, the final trees are all weak learners. With XGBoost, though, we start with a weak learner. Then we look at all the data points the model got wrong and reweigh the importance of these points to be a bit higher than the points the model got correct. After that, we train a new model with those newly weighted values. We repeat the process for some number of iterations. The upshot of this is that we emphasize getting those higher weight values correct precisely because they appear to be the trickier ones to classify. XGBoost was a great idea when it came out, beating bagging as a technique. But then Random Forest emerged as a competitor, beating out XGBoost, and that left Random Forest as king of the trees for a while. Well, at least until roughly the year 2016. Because in 2016, we saw the emergence of XGBoost and the initial release of LightGBM, two libraries built on the idea of gradient boosting. Gradient boosting, at a high level, looks at how far off the prior model was, and then it adds a modification factor to try to make the answers more correct than before in the next iteration. Gradient boosting assigns higher weights to the data points its prior predictors got wrong, similar to what we see with XGBoost. But there's a trick to gradient boosting that makes it so much more effective than just using XGBoost. Gradient boosting starts from a point of ignorance. In the regression form of gradient boosting, we start with the mean of our label as the prediction for each data point. In a two-class classification, we calculate the log odds. So we take the log of the quantity of class 1 divided by class 0. This gives us our log odds. With a simple example, let's say that we have 104 people in class 1 and 114 people in class 2. That would give us a log odds of negative 0.04. Then we could take that log odds and convert it into a probability using the following formula. For our initial round, we have a value of 0.49. By default, we have a threshold of 0.5, where if that probability is below 0.5, we mark the value as a class of 0, and if it's above, we mark it as a class of 1. We can change this threshold as a parameter, but for the moment, let's just keep it at 0.5 and keep things simple in our heads. We are below 0.5, even if ever so slightly. Therefore, we would assign class 0 to every element of the training, which would mean that we'd be right 114 times, but we would be wrong 104 times. But what's interesting here is that we're calculating the residual, not just the class prediction. In other words, we're seeing how far off each prediction was from that initial guess. This residual is what we use for the next round of prediction, not the actual classification itself. We then use a transformation function that allows us to combine results from that first tree and the second tree together, and we use a learning rate that's fairly close to 0, which means that we're going to get marginal changes, not enormous world-breaking changes immediately. This is where we get the name gradient in gradient boosting. Now, XGBoost and LightGBM, they both work a bit differently in terms of how exactly we grow the trees and how they change through the training process. My aim in this series is to keep things at a pretty high level, so I won't go deeply into the math behind either algorithm, though I will give you some links to the original papers, as well as some explainers that I found helpful along the way. What I will say about this, however, is that we ought to compare random forests and gradient boosted trees. Remember from the prior video that a random forest is a collection of independent trees, each of which is a weak learner. We average the predictions of all of the trees to get our final prediction. By contrast, gradient boosted trees, whether you're using XGBoost or LightGBM or even some other algorithm, these are also a collection of trees, but they are sequential trees. What this means is the latest tree will depend on the prior tree, which itself depends on the prior tree, and so on until we reach that first tree. This is still an ensemble technique, but we're building things up. Showing this idea of boosting in a simplistic image form, and kind of showing you the idea behind ADA boost rather than gradient boosting, I have some original data, and I'm trying to classify that data by color. I send the data to my classifier and get some correct predictions and some incorrect predictions. Then I train a new classifier and reweigh the data points I got wrong, giving them a higher weight than the ones I got right. Pass that into the new classifier and we'll get a new set of results, which hopefully gets more things right than before. We keep doing this over and over, building more and more sequential trees that try to get more things right. Basically, we have a montage sequence in tree form. We're doing the equivalent of punching slabs of beef and running upstairs, getting our tree in fighting shape. And with that idea in mind, let's go 12 rounds against Apollo Creed in the demo. For this demo, I'm going to show two separate notebooks. This first one will use XGBoost, or Extreme Gradient Boosted Decision Trees. XGBoost is the most popular form of gradient boosting out there, and that's because it does a really good job on a variety of problems. The import statements look very similar to the first couple of notebooks, except that we are importing XGBoost as XGB. Scrolling down a bit, we have exactly the same data set as we used in the first two notebooks, so we should be able to develop a fair comparison between techniques. Let's load that data and continue on. We're also going to do the normal Python supervised learning thing of creating X and Y variables containing the features and labels respectively. Then we'll split these into training and test subsets. I'm using the same random state and test size in all of these notebooks in order to reduce the effect that training and test data selection might have on our results. Classification via XGBoost is a little different from how we've done it in scikit-learn, though only a little. We create a new XGB classifier, passing in a few parameters. We set the maximum tree depth to 5 and the maximum number of estimators to 45. As a quick note, I did try a variety of values for max depth and number of estimators, and this combo seemed to work consistently well for the dataset. I am using negative log likelihood as the evaluation metric. There are a couple of other options for evaluation metrics when dealing with binary classification, though with this dataset, switching the metric didn't appreciably affect accuracy. After creating the classifier, we fit it in the same way we fit other algorithms so far. Then, for prediction, we can use the same code to predict and then calculate the accuracy score. The accuracy score for this algorithm consistently runs in the 81 to 84% range, depending on luck of the draw, putting it right in the same neighborhood as random forest and a good step above cart. Also, one nice thing in XGBoost's library is its ability to generate an importance plot. Unlike what we get with GraphViz against cart trees, This gives us a quick analysis of which features are the most important to classification. I will run this, plotting the 7 most important features according to our model. The most important feature in this dataset is age, where older people are more likely to have long-term heart damage. The next 2 most important features are maximum heart rate achieved and cholesterol level, respectively. Then there's a dip, and there are a few other measures that are not quite as important as these 3. Now let's see how we can do the same thing with LightGBM. The light gradient boosting machine algorithm, as I mentioned before, is another example of gradient boosting, one that Microsoft Research released in 2016. You can install it using the LightGBM pip package. Our import statement is almost exactly the same as XGBoost's, except that we're importing LightGBM as LGB. I'll quickly load the dataset and separate it out into X and Y variables. Then we'll split the data into training and test datasets, again using the same random state to get the same splits. Now let's look at how we train the model. We call the LGBM classifier method and can send in a variety of parameters. I've set 3 of them here: the number of leaves, the max depth, and the number of estimators. The number of leaves is how we control the complexity of the model. We can also set the maximum depth, which is how many levels deep our terminal nodes reside. As a quick note, we generally want to set the maximum number of leaves to be smaller than 2 to the power of max depth. In this case, 2 to the power of 5 is 32, so we want to set the number of leaves to be smaller than 32. This helps us avoid overfitting and optimizes accuracy. As a quick note, if you set the number of leaves to 31, you'll actually get a warning because the default is 31 and the library will think you didn't actually set a value. The end result will be very similar in terms of accuracy in this case, but I'm going to go a few leaves below that anyhow, just to make sure I don't get that warning. We can also set the number of estimators, which is the number of boosted trees to fit. After a bit of testing, I settled on 45, which is the same as what we saw for XGBoost and consistently gives me good results on this dataset. In most cases, LightGBM gives me an accuracy of approximately 83.5%, and there's been very little variance so far for me. Of course, that's no guarantee that it will always give you 83.5%, but it does seem a bit less susceptible to luck of the draw than some of the other algorithms we've looked at. Also, we can generate a feature importance plot for LightGBM as well. Our top 3 features are still the same: age, maximum heart rate achieved, and cholesterol level. But we can see that there is a tighter band for features, where we still see the hierarchy of feature importance, but they're all within a tighter band than what we saw with XGBoost. And that was the duo of XGBoost and LightGBM, 2 of the most powerful gradient boosting techniques. So far in this series, we've seen several tree-based techniques and compared their results using accuracy as our primary, only measure. In the next video, we will see why accuracy is not always enough, so definitely stay tuned for that. We'll have links and show notes in the description below, and until we see each other in the next video, take care.